Well, welcome everybody. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing. I'm excited that you're all here to join us for the World Above the Teton Speaker Series presentation tonight with Suzanne Gurton. Just want to give a shout out to all of our sponsors, especially the members of the Wyoming Stargazing Board of Directors who helped to make these programs possible. We couldn't do it without their help, so thank you very, very much. Definitely hang out after the presentation this evening. We'll do a Q&A after Suzy finishes up her presentation, but then we're going to do some door prize drawings and a raffle drawing for those of you who've purchased raffle tickets. We've got some cool stuff to give away for both of those after the presentation. So definitely stick around for that. And anyone who's here is entered into the door prizes. So you've all got a ticket in the bin right now. And for those of you who just showed up and will show up later, I'll put a ticket in there for you as well. So we're really lucky to have Suzanne Gurton with us tonight. She is the Assistant Director of the National Radio Astronomy Observatory, overseeing their media education and public outreach efforts. She oversees a creative team of artists, writers, and educators to tell the story of the invisible universe that is uniquely revealed by radio observations. And that's what she's here to talk with us about tonight. And so, Suzy, we're all yours.
Okay, thank you. I'll start sharing my screen here. Go into presentation mode. Okay. Well, thank you. Yes, I've had, I like to think of it as kind of a double rainbow career. I spent the first half of my professional life working in the planetarium field and starting out as a student worker and then eventually becoming a planetarium director. And then I switched to working in education at a nonprofit that was in the San Francisco Bay Area, the Astronomical Society of the Pacific. And all the different experiences that I had, I've lived an awful lot of different places, but it all added up to something that gave me the bravery to apply for this job of assistant director at NRAO. And I have just such a creative team that I work with that it's, I always sort of fight back this urge to just be a fangirl. I've loved astronomy my whole professional life. And so now working at a national observatory is really quite an honor. And I don't want to make it out like I'm a PhD astronomer. I've never been a research astronomer. I've always been the storyteller. So what you'll see today is kind of an overview of our facilities and then some of the discoveries that they've made possible. So let's get going. This first image, in my hopping all around in my planetarium career, I was in Colorado for a couple of years at the Fisk Planetarium in Boulder. And I had the opportunity to go up to the W Tower. This by no means is one of my photos. It is credited down there with David Lane. And I have to say that these kinds of images do so much to just capture people's imaginations in looking at the night sky. But in some ways, they're deceptive because really you only see this kind of detail with the unblinking eye of time exposures. So I'd like to find out a little bit about how you like to observe the sky. I didn't ask you if we could do this, but it looks like the annotation is live on here. So if you all are familiar enough with Zoom, if you go up to the top of your screen and you can click on annotate and stamp, you can choose a shape and tell me what your favorite way of observing the night sky is. Are you all just going out with your naked eye, enjoying the wonder. That's certainly one of my favorite ways of seeing the sky. Or do you use binoculars? Do you use reflecting telescopes? What's your favorite? I'll give you a minute to figure out how to use the annotate feature. Okay, we're getting a few votes down on the naked eye and a couple for binoculars and only one for the reflector. Okay, I didn't include, you know, anything too sophisticated, and I also didn't include the kind of the armchair variety. If you love learning about it through documentaries or just surfing the web. So it looks like you guys are kind of low tech here. Okay, well that gives me a good idea of how to go forward. Let me clear those. Let me see if I can get my mouse there. Clear those votes. Whoop. Oh, that's interesting. You got them cleared. Excellent. Okay, so let me go back to this one for a minute. You all apparently like to use simple, your eyes and binoculars. At the National Radio Astronomy Observatory, what we like to do is use these amazing, very different kind of eyes. We use these giant radio telescopes to observe the sky. And one of the really exciting things about radio astronomy is that you don't need this kind of clear, dark night sky to do the observations. We also observe in the daytime. Here's a picture of the VLA taken from our webcam. Last month, it was after a monsoon, and you can see a rainbow coming out there. The high arc of the rainbow tells you that the sun must have been pretty low. It was taken just before sunset. And by the way the dishes are pointed, you can tell that we were taking some observations. So radio astronomy works in the daytime, in the nighttime. It's a very different kind of eye that we are turning to the sky. And of course, the kind of eye that you use determines what you see. And I had given a talk like this at a national park, so I thought I would toss in some of what I boned up on to give this presentation. And I was thinking about the wildlife in the national park and how it might see the sky. And so if you didn't have human vision, but if you had deer vision, you would see the world around you a little bit differently. I don't know if any of you are hunters, but you can stay safer while you're hunting by wearing brilliant orange colors, because deer eyes only have blue and yellow receptors in them. So they're not sensitive to the red and orange part of the spectrum. So they see the sky very differently, and it's a good thing for hunters because then they can wear these bright colors to keep themselves safe. Snake vision is also very different. It not only do they have eyes that see in the same colors that we do, but especially the pit vipers have those infrared sensors. And so they can detect heat, which brings different kind of warm-blooded life really to a different kind of, just a whole different way of seeing them than say we would see them or than hunters are seeing them. Bees also see the world very differently. And it's because they are not sensitive to the infrared, but to the ultraviolet. And there's a German photographer who has taken some time to figure out how both bees and butterflies see the universe or the world, the natural world around them. And this image on the right is taken with an ultraviolet filter. The image on the left is how we see the flower. And the image in the center is that bee vision. So they see ultraviolet plus some of the optical. And when you combine that, it's almost like a target saying, right here, come get my pollen. It's a very different way of seeing what to us seems like a monochromatic flower. They see very differently with that target. So the kind of receivers, the kind of receptors that you have influences how you see the world around you. And this was just a little comparison where the bees are seeing, they're sensitive in the yellow, and they go through the blues and purples, but beyond the purple into the ultraviolet. Humans see the regular rainbow of colors from red to violet, and the infrared is up here. That's what the snakes add to their vision of the universe. And NRAO has 3 very different sets of eyes that we turn to the cosmos. This one, I know you're not supposed to have a favorite, but I have to admit that this one is kind of my favorite because I get to go out when we are allowed to travel. I get to go out and see it the most, and that is the Very Large Array out in New Mexico. We also operate the Very Long Baseline Array, which is a very different kind of telescope. In many ways, it's similar to the VLA, similar size dishes. But I couldn't show you a single picture of it because it is 10 dishes, 8 of which are scattered across the continental US. 1 is in Hawaii and 1 is in the Virgin Islands. So this continent-wide array gives us just unprecedented resolution. And we'll get into a little bit more of that in a minute. The third observatory that we run, we are the North American partner for the international partnership that has created ALMA, the Atacama Large Millimeter Submillimeter Array. And I have to say, I always laugh at that name because millimeters are not large. It's a large array that observes in the millimeter and submillimeter wavelengths. So let's take a closer look at just what part of this whole broad electromagnetic spectrum our observatories are sensitive to. So this is a slide that I borrowed a couple of slides from one of our astronomers who was recently giving a presentation, and I liked how this gives such a nice overview of our facilities. So you see here the rainbow of colors that our eyeballs are sensitive to. Then you have here the ALMA array, which is sensitive to the millimeter and submillimeter wavelengths. The Very Large Array in New Mexico goes into the centimeter wavelengths, and the VLBA overlaps those a little bit. It sees a little bit higher frequency than the VLA, but it doesn't go as low as the VLA. Let's take a look at just what we're talking about here. Remember that light is, I've been using that phrase interchangeably between light and electromagnetic spectrum. The electromagnetic spectrum, remember, is 2 waves. You've got the electric wave and the magnetic wave, which is perpendicular to that. And the wavelength is the distance between 2 crests in those waves. And the wavelengths that we can see that our eyes are sensitive to are down in the nanometers. And what the VLA can observe in, go back there. What the VLA is sensitive to is like a foot-long wave of light. There's no way that's going to fit in your eyeball, right? So of course we can't see in radio. It goes from a foot down to 1/4 of an inch. And ALMA is in much shorter, so it's in the millimeter and submillimeter wavelengths. And I don't know if you can see it right over here. There's a little squib right there that is about 3.5 millimeters. on this ruler that is up at the top here. So it's much shorter wavelengths, and we'll see later on as we talk about the discoveries made possible by these observatories that they're looking at very different phenomenon because we're looking in very different wavelengths. And the idea behind these, I won't spend a lot of time on this because you're not big telescope folks, but I thought I would draw the comparison between an optical telescope and a single dish radio telescope. And here we have a basic Cassegrain kind of alignment where you've got your primary mirror. The light comes in, bounces off your primary up to a secondary, and then it comes down here. And at that point, you could put a different kind of receiver there. You could put your eyeball to receive the image. You could put a camera, a CCD. You could even put filters in there to get different perspectives on what you're observing, to see different sensitivities, enhance different details. And if I was in a hurry, I would just do the same thing on this picture, but let's just take a moment to look at this because I'm proud of our multimedia team. They have created quite a few interactives on our website. And this one is an overview of a VLA dish. So as you roll around on here, you'll see different details. You can also start over here. So it's a little less hectic if I start with the words. So you can imagine that radio wave, which is a light wave, coming down, hitting the surface of the dish, bouncing up, coming to a focus at what we call the subreflector. So with your optical telescope, you would call it your secondary mirror. But here we call it a subreflector. And from the subreflector, it goes down into feed horns. And in a minute, we'll get a closer look at some of those feed horns. The feed horns are almost like filters, the radio analog of filters from an optical telescope. And you can see here that there's a variety of different feed horns in there that then take that focused image down to a receiver where it gets amplified and sent off to a supercomputer that will combine the images from all of our different dishes. To give you a sense of just how big this is 82 feet across, and it's about as tall as a 10-story building. Let's go back to this one for a minute. So just to give you a comparison of the different sizes of dishes that we have and the difference that they make. I'll make some comparisons to optical telescopes here. With an optical telescope, you think about light gathering power, right? And I saw there were a couple of votes for the reflecting telescope. I don't know if any of you have ever caught that aperture fever and wanted just bigger and bigger telescopes. Well, professionals have the same problem, and they want bigger and bigger dishes to catch more and more of those photons. Now, the way we deal with radio waves is not the same as counting photons, but for now, we'll use that analogy. And what you can see here is the largest steerable radio dish on the planet is the Green Bank telescope. Imagine just picking up an acre of land and pointing it at whatever you want in the sky. That's Green Bank. Our origin story for NRAO is one that started at Green Bank just 4 years ago in their infinite wisdom. I do not know all of the reasons behind it, but the National Science Foundation, who is our funder, decided to make Green Bank an independent observatory. So Green Bank Observatory is no longer managed by NRAO. But it's a really great point of comparison, because what you see here is the area of the Green Bank telescope, which is the largest steerable radio dish on the planet. And then you see our other little dishes. So that VLA dish is just 25 meters, 82 feet across. And the ALMA dishes here are 12-meter dishes. And as a comparison, one of the behemoths of the optical world is the 10-meter Keck telescope. So you can see there's the Keck, there's ALMA. This is dreamland here. We haven't invented the NGVLA yet. I'll talk about that at the end. And the 25-meter VLA and VLBA dishes. Oh dear, I have a feline companion who may walk through here. One of the advantages of having that bigger light bucket is not just being able to see dimmer things, the light gathering power, but also being able to resolve finer and finer details. So one of the images down at the bottom here is the way that astronomers talk about that detail is in arc minutes or arc seconds. And while we're talking about a single dish, you know, these 12 and 18-meter dishes, the resolution is also proportional to the wavelength that you're observing in. And one of the major challenges in radio is that we're observing such long wavelengths compared to these little tiny optical wavelengths that you need bigger and bigger dishes to get decent resolution. So as we look at this chart, it's just kind of heartbreaking. No wonder our images are fuzzy. When you look at the Keck, right, it's observing in tiny wavelengths. Well, that means it has great resolution, less than an arc second. So 360 degrees in a circle. 1 degree has 60 minutes in it, and 1 minute of arc has 60 seconds. And it can see 0.2 arc seconds. That's just remarkable, just exquisite resolution. Well, our VLA dishes observing in the centimeter wavelengths can see 4 arc minutes of resolution. That's not so great, but we have a way of overcoming that. And let's take a look at some of our some of the next slides. You can also see that, like NGVLA, what, you're dreaming of 5 arc minute resolution? No, no, no. We're really dreaming big with the NGVLA, and we'll get to that at the end. The variables that we have in talking about a radio telescope have to do with what frequencies we observe in. So that's the inverse of the wavelength, right? So we talked about the millimeter versus centimeter of ALMA and VLA, but also the frequencies have to do with these feed horns here and the receivers that they will channel that signal down to. I've only gotten to climb a VLA dish once, and I told a friend of mine who is an astronomer for the Hubble Space Telescope about it, and it turns out early in his career he had a chance to do this, and he's 6'5", and he said he was so excited when he got to go in there, but it made him feel small. He said he felt like, and I've just never forgotten this, the last cornflake in a giant cereal bowl. I just love that analogy. So you can see these guys here, they are being careful to stand along the seams of the dish where it's a little bit stronger. And some of these feed horns are huge. You can see that's a human-sized feed horn there. Some of them, they do have to move in giant trucks. And that's for the longer wavelengths. For the shortest frequencies that we, or excuse me, the highest frequencies, the shortest wavelengths that we observe, those feed horns and receivers are much smaller. The ALMA ones I can hold in the palm of my hand. So this is almost like putting a filter wheel in your optical telescope, you can decide which of these feed horns you're going to send that signal down to. And this, what we would call the secondary mirror for an optical telescope, the subreflector in the radio dish actually moves. And so the waves bounce off of the big parabolic dish up to the subreflector, and then that subreflector can rotate around based on your chosen receiver. So that's one of the variables that we have. The sensitivity has to do with how many of our, well, has to do with both how big our telescope is and how many, in this case, how many dishes we have out there. But also it has to do with the quality of the electronics. And we're coming up on our 40th anniversary of the VLA this October, the 40th anniversary of its dedication. It took a few years to build. It was built in the 70s. And it's, when it was built with 70s technology. And we have completely gutted these and given it new electronics. Instead of using waveguides, we have fiber optics. And basically it became a whole new observatory. And by 2012 is when we had finished the complete upgrade of the VLA. So just by improving the electronics, we improved the sensitivity without having to add more dishes to the array. In this next picture, I talk about the resolution. So we had talked about the resolution of a single dish, but we can improve our resolution in radio astronomy by not just adding dishes, but spreading them out and then using a supercomputer to combine all of those signals. So we can pretend that we have one giant dish that's 22 miles across at its most, at the highest resolution, right? And we have kind of a fun little interactive here where you can find out just what configuration is the VLA in now. And so if you go to this web page, you can see we are currently in the B configuration. And I'm going to take just a minute just because this is so much fun to play with. We're in the B configuration. Will take about a week to stretch out that northern arm into the A configuration, and I'll tell you why in a minute about that one. When we go to the A configuration is when we're at our most extended arms. The D configuration is when it's at its tightest. So what we've done here is zoom in to the tightest configuration, and this is where you can see our grounds. NSF actually only owns a square mile out on the plains of San Agustin there. And when we're in the D configuration, all of those dishes are darn close together, and this little building here is our service barn. So there's actually 28 possible dishes in the array, but one is usually in the servicing barn. So we're always rotating through doing regular service on one of those, rotating through. So only when we're in this D configuration do you really see our full grounds here. With the barn, there's our little visitor center that someday I hope we can welcome you to again. And this is the control building that the operators are in, and some of our shops are out here. And I'm going to encourage you, I'll share all these links at the end of the presentation, but I'll encourage you to goof around with this, because as you zoom in, you can see that in the Google map, this was, there actually was a dish here. So the ones that have shadows, there actually were dishes in those spots, but where the blue ones are is where it is for the D configuration. So when Google took these pictures, we were not in the D configuration, and I'll let you play around with it to figure out which configuration we were in. Each one of the configurations is 3 times bigger than the previous. So our A configuration is when we are at our longest and with our highest resolution. So by adding 25 dishes, or excuse me, 27 dishes for the VLA, we now have the light gathering power that is well beyond that of Keck. It's even better than the sensitivity or the light gathering power of Green Bank. And it's even better than ALMA. Even though ALMA has 66 dishes, they are all smaller than our 25-meter behemoths. So the sensitivity or light gathering power of ALMA is smaller. And this is a hint about how we are dreaming big for the NGVLA. But over here, you can see that one of the reasons that we have the 27 dishes and the A configuration is to basically get comparable resolution with the VLA to the largest optical telescopes like Keck. So now at that 3 centimeters, even though we're at much longer wavelengths, by being able to spread those arms out to they're 12 miles long each, about a 22-mile diameter, we have the resolution that is comparable to optical telescopes. And when you look at the VLBA, it's not as sensitive because it's only the 10 dishes, but because it's spread out over so much larger an area, you can see that it has a fraction of a milliarc second, which is pretty cool. And wait until you see some of the discoveries that have been made possible with it. And just to give you a feel for how, this isn't quite interferometry explained, but it is a fun way to, let me see, how are we doing on time? It's a fun way to have some, get a feel for how the interferometry works. I'm not actually going to click through this because I want to get on to our discoveries. But at this link, you can choose a picture, choose a configuration. Here I stuck with the Y and I went with small to begin with. So you would see all of those go in and then you make an observation. And I just took a 10-minute exposure of what looks like a pretty empty piece of the sky here, an image. And this obviously is not a real piece of the sky. The resulting, we have the Python on our server, so when you click that, it actually goes through and does the interferometry to analyze that image. And you can see it says messages in the background with some big bright blob here in the center. That's because we're at our small configuration, which is the lowest resolution. So I did it again, stretching out those arms to its highest resolution. And now you can resolve the detail in that blob to see that it says secret messages. So we have the different configurations to reveal different kinds of details. We have different frequencies, just like we might use different filters to reveal different details. So that is a really zoom quick overview of our 3 facilities and some of the variables that we have to work with as we make our observations. So sometimes I'm jealous of you with your gorgeous night skies, clear dark skies, where you can see beautiful moons, planets, stars, constellations, pull out those telescopes, see your nebulas and galaxies. It really inspires just an incredible sense of wonder about the universe. It might inspire some of those very deep questions about our origins. But when we turn not our human eyes, but our radio eyes to the night sky, we don't see it filled so much with this as with magnetic fields, black holes, and just mind-boggling violence is revealed when we look in radio. And in fact, we are using the VLA right now to map the entire sky And we're in that B configuration. So it's pretty high resolution, not the highest resolution, but pretty high resolution. And what do we see? We see a sky full of galaxies with supermassive black holes in their center that are shooting jets out on both sides. And all of these images are from the VLA Sky Survey. I hope in the not too distant future that we'll actually have some programs. We've got some good student programs going now where we're teaching students how to go in and take out little slices of the VLA Sky Survey and do some analysis on these images. It really is being created as a gift to the community, to the astronomical community. It's at such high resolution that it's just unprecedented. One of our previous sky surveys was done when we were in the D configuration, which is the lowest resolution. Enough to say, oh, there's something there, but it was just a blob. In the optical, when you look at that same part of the sky, you don't really see anything there. In infrared, maybe? I mean, there's kind of a hint of something in there. But now with the VLA Sky Survey, this time around, being in that B configuration, it's just unprecedented resolution that we have. And now that green blob is being resolved into this pair of jets, which let us know that there is probably a supermassive black hole at the center of a galaxy there. And that's what that previous image was, is that the universe is filled with these radio galaxies. And you just wouldn't have a hint that they were even there until you looked in radio. And literally, I mean, there were just so few examples of strong radio sources before that when we turned on the VLA 40 years ago, we saw things that had never been seen before. Now, this is kind of exotic. I want to start talking about some of our observations, and I want to start on a little bit more familiar ground. Let's start with the solar system and beautiful Jupiter. Jupiter is just gorgeous through, even with a pair of binoculars, Jupiter is gorgeous, right? You can see those Galilean moons. Well, when you look, this is with the old VLA. So this was before the upgrade, and that we call the EVLA. But you could map it out, and the planet is here, but we're seeing radio sources off here and kind of a belt going across here. Well, it turns out this is not unlike the Earth's own Van Allen radiation belts. Jupiter has a very similar structure that is very clearly revealed in radio. And when comet Shoemaker-Levy 9 hit Jupiter, it changed that magnetic field. You can see that there was all sorts of disruption. So this is before comet Shoemaker-Levy 9 and after Shoemaker-Levy 9, after that collision. Amazing details were revealed. And here is a little video that we put together looking at Jupiter, but not with the VLA eyes, but with ALMA. And by looking at much shorter wavelengths, higher frequency, there's a whole different level of details that are brought through. And I forgot to check audio when we did our check. So let me know if you can hear this okay. Uh-oh. My internet has slowed down.
We're not getting the audio with that, Suzy.
Oh, that's disappointing.
You can usually get it going if you unshare your screen and then share again. Just click the share computer audio in the bottom left-hand corner of the share window.
Okay, let's try it again. It looks like something might be going wonky with my internet. I'm starting to get that
Okay.
little, let's hope not. Okay, share computer sound. Let's try it again.
19 top 10 countdown of ALMA observations. You might recognize this object as Jupiter, the biggest planet in our solar system. If it looks a little odd, that's because this isn't a visible light image, but one taken at the much longer wavelengths ALMA sees. The image shows the stripes of Jupiter, called belts and zones. In visible light, zones are bright and belts dark, but to ALMA's eye, that's reversed. Zones are at a lower temperature than belts, and at these wavelengths, ALMA senses the temperature of the gas, so the cold zones are darker and warm belts lighter. ALMA observed Jupiter just a few days after some large storms erupted from deep within the atmosphere. ALMA can detect gas down to 50 kilometers below the cloud tops, allowing scientists to make a 3D map of the way the gas moves inside Jupiter's atmosphere. They could see how air laden with ammonia and water vapor rises, cools, and flattens out when it reaches the tropopause, the coldest layer of Jupiter's atmosphere, much like massive storm clouds do on Earth. Jupiter's atmosphere is in many ways alien and complex, but ALMA is showing planetary scientists that there are some similarities to Earth, and that helps us better understand both worlds.
Okay, so ALMA gives us a very different perspective on Jupiter, and let's keep going because there's lots of other observations that I want to share with you. ALMA also took a look at Uranus, and one of the things that I've loved about working with our press group is that we discovered that sometimes astronomers are looking for one thing and they find something else. And that was true with this Uranus observation. They actually were trying to look at the clouds of Uranus, just like in that previous video, we were looking at the clouds of Jupiter. They wanted to look at the clouds of Uranus. And I said, wait a minute, we can see the rings. They weren't intentionally observing the rings, but it turns out that the rings are right at about 77 degrees Kelvin. And that is the temperature where liquid nitrogen boils. And that temperature just helps them understand more about the composition of the rings. They can do spectroscopic studies with that, but they did not think that they could see the rings with ALMA. So they were surprised that they saw this little glow here. In addition to planets in our own solar system, one of the things that ALMA is quite famous for, there we go, is looking at planets forming around other stars. And I would say that probably this is the image that is the iconic image that everybody first associates with ALMA is HL Tau. And so this was looking in the constellation of Taurus. And optically, you see it, optically, we don't have the resolution to see what ALMA is seeing. So it's dusty. And it turns out that in radio, you can see through a lot of the nebulosity. And in this case, these amazing rings were revealed in what's called a protoplanetary disk. So the star has turned on, it has started to shine, and there's this dusty disk left around it. And this was the first time we could see all those gaps in HL Tau. And it's probably, I would say it's probably the most famous image from ALMA, although I'm going to share some other mind-blowing ones with you. In addition to seeing just these grooves, these gaps where planets are forming, we've also seen the first, not just circumstellar disk, right? This is a protoplanetary disk where planets are forming. So it's circumstellar, it's a disk around the star. This little blob right here is the first time they saw a disk around a forming planet. So we not only see planets forming, but that could be where moons are forming. One of the other crazy things that ALMA has revealed is that we thought that places like Teton were pure science fiction. I'm old enough, old school enough that I thought, it's like, nah, that's all science fiction, right? You're not stable enough. We can't find a stable place. If you've got two stars rotating around each other, you're not going to have a stable enough environment for planets to form. Well, we were wrong. ALMA has discovered several of those. And in fact, one of our latest press releases is about a triple star system, thank you. Not just a double star system, but a triple star system. And one of the fun things that our multimedia group is doing is creating augmented reality experiences. So on my laptop, you can see it here and you can move it around, the 3D model. If you are on your phone, you can, and that's why I put this up here. If normally I ask people not to have their phones out while we're doing a presentation, but if you go to that link, you can use the QR code down in the corner there and look at it. You can actually have that triple star system here in the room with you. You can see it through the camera of your phone and bring it into the room with you. We've done that for our telescopes too. So there's all sorts of fun stuff on our website that I'll encourage you to explore. But with this one, the really cool thing about this discovery is that it's the first time we've seen a planet forming disk around a triple star system. And this one ring is not in the same plane as the other. So all three stars are in the center there. And they think that that third star has disrupted the planetary formation. And there's this one that is off at a weird angle. This was not just ALMA observations. This was combined with some other observatories. Back when I was first working at the Astronomical Society of the Pacific in the Bay Area, we had a great contract to work with NASA to develop something called the NASA Night Sky Network. And that Night Sky Network was initially funded by the group that was looking for planets around other stars. And we did a whole toolkit about how to find planets around other stars. And the big method was the wobble method. And the wobble method, you may recall, was when we were first finding planets because they were pulling and pushing on the star that they are orbiting. So there was a red shift and a blue shift to the light coming from that star. So we weren't seeing the planets themselves, we were seeing their effect on the star that they were orbiting. And we said, one day we'll be able to look for transits. Well, that's what Kepler is doing, right? And suddenly the number of planets that we know around other stars has just exploded. And there's enough statistics there that it's pretty obvious that planets are a pretty natural byproduct of star formation. And we used to dream that one day we would have the sensitivity to actually see the physical motion of that star as it's getting jerked around by its big planets. And that, my dears, is what the Very Long Baseline Array did recently. This is a little animation that our team put together that is showing, this is a very small, cool star, okay? And so it's much smaller than our sun. It's a little red dwarf. And this, it's less than 100 times the mass of Jupiter, in fact. It's a very small, cool red dwarf that glows brightly in radio. So in using the VLBA, we were able to see this star. And because it's the VLBA, with that incredible resolution, we were able to measure the changing position of the star as it got jerked around by that large planet. So that is a Saturn sized planet that in comparison to its parent star, is so massive that the star and planet system, the center of mass of that system, is not inside the star, but outside the star. So as the planet is orbiting, it is actually pulling the star around, and they were able to observe that change in position of the star with enough accuracy to determine how big the, that there was a planet in orbit around it. So that was a mind-boggling one, thank you, by the VLBA. I only have a couple of VLBA observations for you, but from my perspective, they were all kind of mind-boggling. It required just exquisite resolution of a continent-sized radio telescope in order to make that measurement. So now let's look at something a little more familiar, good old Orion. And the Orion Nebula M42 is part of a much larger complex that is the Orion star cloud. And John Tobin, who is one of our NRAO astronomers, working with a team, has used both ALMA and the VLA to look at these very young disks of protostars. So these are places where stars are just forming, and they're starting to be able to understand and discern which are younger protoplanetary disks and which are older protoplanetary disks. So clearly the more massive ones are the ones where the star hasn't turned on yet, because there's so much material left over in the disk. The older ones will have accreted that material. So with ALMA, they're seeing the dust, and with the VLA, they can see through that dust to that brand new baby star that's at the core. So this is an amazing study. This is just the first look at that data. I fully expect some wonderful papers to come out of this survey, where they're combining both the ALMA and the VLA data. I also wanted to share some observations of something that it's like you can just look up in the sky and see that, right? Antares, the heart of the scorpion. Antares is a huge red star, and when we observe it with ALMA, you see beyond where you would see with just optical. And with the VLA, you see beyond that to see the stellar wind that is being blown off of this giant. So here we thought we knew, so much about Antares. In this artist's conception, we can show some of the details that are brought out with our radio observations. So our sun would be at the center of this drawing. The edge of the surface that you see when you look up at the night sky is called the photosphere. The edge of the photosphere is about 700 times that of the sun, right? 700 times the diameter of the sun, which brings it out past the orbit of Mars, almost about halfway to Jupiter. With ALMA, we can see the lower chromosphere and into the upper chromosphere, which is that really roiling part of the star's atmosphere. And then with the VLA, we see beyond that out into the stellar wind. So we're looking at young stars, we're looking at old stars, and we're looking at blown up stars. So supernova remnants are kind of, how am I doing? Oh dear, okay, I'm running out of time. Let me, I'll speed it up a little bit here. I'll get on to just a couple things. This is Cass A. I wanted to show this one just because it's in Cassiopeia. Very familiar, easy to find constellation. And the image on the right is with Spitzer and Chandra, and on the other side is the VLA. So similar structures at very different detail. And you can see that a lot of the X-ray is the Chandra. This is the Chandra data. And this part up here is some of the infrared, and you see that some of that is very similar to what we're seeing with some of the radio structures. And the most important point of all of this is that all of those are wavelengths that you can't see with your eye. So all of this detail is revealed in wavelengths beyond what our eyes are sensitive to. The supernova of my lifetime is 1987A, and there have been several observations by ALMA. This thing is just a crazy supernova. We thought, right, when you think you understand something, we get one that is so close, it's great to observe, and we looked at it and it's like, wait a minute, that star that blew up shouldn't have blown up. It was a blue star. Shouldn't it be a red star that blows up at the end of its lifetime? So there were all sorts of odd things about supernova 1987A. And one of the lingering mysteries is what's left over. Was it big enough that the core collapsed into a black hole, or was it a neutron star? Well, it's been pretty dusty. And twice now, we've had some ALMA observations that have astronomers pretty well confirmed that what is causing that dust to glow is a neutron star remnant. I'd like to say mystery solved, but we're still just looking at the dust. They're pretty certain, but not 100%. When we look at the center of our own Milky Way galaxy, we see all of these other supernova remnants, all of these things that look like bubbles. This is a map of the center of our galaxy from the VLA, and all of those bubbles are supernova remnants. But the part that I wanted to show here is something that I referred to in that very first observation of Jupiter, is that we can reveal the magnetic fields. So just like if I had a piece of paper here, or if I had two pieces of paper, one was over a magnet and the other one wasn't, how would you know where the magnet was? Well, if you toss some iron filings across it, those iron filings organize themselves according to the magnetic field over the magnet, and they would just be random over the piece of paper that doesn't have anything underneath it. So those iron filings reveal the magnetic field. Well, here we have all sorts of charged particles spiraling around the magnetic field lines at the center of our galaxy, revealing the magnetic field there. We've also looked at galaxies outside of our own. This is an amazing image taken by Diane English, who is an astronomer up at the University of Manitoba. And this is in Canes Venetici. It's right near M106. It's an edge-on spiral galaxy. And in looking at the polarization data from the VLA, these magnetic fields of this external galaxy are revealed. It's not only magnetic fields, it's also mapping out gas that gives us some amazing information about some very familiar objects. Good old Whirlpool Galaxy. If I could see you, I have you all minimized there. I mean, I don't know if you've seen this through a telescope. It's just one of my favorites because I'm kind of blown away at the amount of structure that you can see with these, that it actually looks like a whirlpool. You can see the dusty lanes and just gorgeous structure in here with just an optical telescope, right? I mean, with your backyard telescope, you can see some stunning structure, and you see both of these. Early on, there was a lot of controversy. Have those two galaxies actually interacted? You know, or are they just lined up in the right line of sight? Well, now we know they're interacting galaxies, and when with the VLA, we map out the cold gas around this, it goes way out here, and we see evidence of the history of the interaction of these galaxies, because that cold dust was torn off and distorted. So it's well beyond the nice organized little sparkling stars that we see here. The gas extends far out beyond that, and it helps us run back in time the history of the interaction between those two. And as long as we're talking about galaxies, here are the radio galaxies that I was talking about earlier. And Herc A is one that just, did you hear that sigh? I just love Herc A because this particular image is one that explains the power of the VLA. We took the time to map out these enormous jets with all 4 configurations of the VLA. So this is the D configuration that you see over here. That little D configuration is when they're all in darn close. You can see big details, the fuzzy gas. It's almost like I gave you a piece of sidewalk chalk and said, here, go ahead, draw those gassy jets with sidewalk chalk. Well, then we stretch out the arms to the C configuration, and you're starting to see some of the tight details here. Out to the B, and finally the A, it's like I've given you one of those super sharp drafting pencils, and you can just pencil in incredible little naughty details in this jet, and you can see some of the swirly characteristics here. This particular set of images is a layer, a composite of Herc A taken with all 4 configurations of the VLA, added to a picture that was taken with the Hubble Space Telescope. So here, when you look with Hubble, you've got those spikes, diffraction spikes from stars that are in our own galaxy. Right, kind of the dirt on the window as we look beyond those stars to this cluster of galaxies in Hercules. All of these objects are other galaxies, and this one is the brightest in radio, and it has these incredible jets in it. So that's an indication of a supermassive black hole at the heart of this galaxy that we just wouldn't have any hints about unless we looked in radio. And the expanse of those radio jets is over 100 million light years. So this is not something that happened overnight. This has been developing over hundreds of millions of years to develop those amazing jets in Herc A. This is one. Here, I have a great sense of wonder for this one. And we used to say that all galaxies have black holes. And I was like, well, you know, all the big ones do, not necessarily the little ones. Well, in the last couple of years, one of our astronomers actually took a look at a bunch of dwarf galaxies. And indeed, there are supermassive black holes in dwarf galaxies, but they're not in the center of the galaxy. So the reason she called them wandering black holes is that they weren't at the heart of the galaxy. They were appearing in odd places within the galaxy. So now I no longer qualify it. It's like we have found them even in the dwarf galaxies. So there are supermassive black holes. So the one at the center of the Milky Way is millions of times the mass of our sun. These in these dwarf galaxies are proportionally smaller. They're smaller galaxies, and the supermassive black hole in them is in the hundreds of thousands of times the mass of our sun. And here I just wanted to say it's not always about a pretty picture. Some of the things that we discover are not the result of an amazing image like that beautiful radio galaxy. Sometimes we look at other details. And I want to wrap up, because I am going a little bit late here. I want to wrap up with one discovery from each of our telescopes that blew my mind. These are discoveries that happened in the last 4 years, because I've only been with NRAO 4 years. And this first one is in the constellation of Cygnus. And Cygnus A means it is the brightest radio source in the constellation of Cygnus. And this one doesn't have any audio. This is just an animation. So I'm going to pause this one as it plays. That's the radio galaxy. You can see those huge jets. And one of our astronomers, Rick Perley, who has, I think he was the first postdoc at the VLA, and he is still one of our astronomers there. And he and his son had discovered a radio source not at the center of this galaxy, just off center. And they were checking up on that to see. It was an unexpected radio source, and they were taking a closer look, and they wanted to see if it had changed. And as they looked at the very center, what they found was something that is not quite the Holy Grail, but something that we have been looking for. And that is a dusty torus. So I haven't talked a lot about the phenomenon of just what all is going on in these pictures, but when you have this supermassive black hole, to explain these jets that are coming out of this galaxy, you need this dusty torus. It's acting almost like a nozzle that is shooting out this material. As the material is coming in, it gets swamped and gets shot out. Well, you need to have this dusty torus. And depending on how you look at it, we've also seen similar phenomenon that, so this is for the radio galaxy. And we decided that two other things, quasars and blazars, may be very similar. So we see quasars at much greater distances. So you don't see as much of the structure of the galaxy around it. But we think we're looking into the heart of that supermassive black hole, where that energy source is shooting those things out. And that would be a quasar. So you're seeing over the edge of that dusty torus. And if you're looking right into it, that it's shooting straight at us, almost straight at us, sorry, that's a blazar. So the viewing angle led us to describe these three different phenomenon, which it turns out are probably the same thing if we can see that dusty torus. Well, we have finally seen it using the VLA only on the radio galaxy. So we haven't seen it in all three yet, but we have seen it finally in a radio galaxy. And I thought that was pretty exciting. This next one is an ALMA one. So you can tell by the big orange blur here, it's another protoplanetary disk that we're looking at. But this is a mind-blowing observation that is not about the pretty picture and the dark grooves in it. This is another video that Phil Plait, that astronomer, narrated for us from last year, one of those top 10 discoveries. This, I don't know if it'll blow your mind as much as it blew mine, but I was amazed at the precision of the measurements that they were able to make to describe the motions of the gas.
From NRAO, it's the 2019 Top 10 Countdown of ALMA observations. There's a disk of gas and dust spinning around the newborn star HD 163296, and the star isn't alone there. 3 planets orbiting the star have been detected by ALMA, their gravity sculpting gaps and swirls in the disk material. The disk is loaded with carbon monoxide gas, which glows brightly at the long wavelengths ALMA detects, allowing astronomers to map this gas with unprecedented clarity. Using this data, they can analyze the 3-dimensional structure and velocity of the gas. What they found was startling. Gas flows along the top and bottom sides of the disk toward the gaps carved out by the planets, then falls down the edges of each gap toward the still-forming planet, like a river flowing over a cliff. It's a gas waterfall. This type of flow has been theorized since the 1990s, but never seen before now. Because of these ALMA observations, we're witnessing the creation of planetary atmospheres. Discoveries like this help us understand how the planets in our own solar system formed, including Earth. Sometimes we have to look up into the sky to understand what once happened, beneath our feet.
Okay, none of you have your audio on, but I hope that blew your mind. It blew mine that we could actually measure the speed, the motion of the gas in those gaps going down, forming an atmosphere, potentially forming atmospheres in those planets. The BLBA discovery that I want to share with you is actually at an accessible part of the sky. It's looking at ARP 299, and TDE means a tidal disruption event. So earlier we saw some of those amazing radio galaxies with those huge jets. Well, this is actually watching the birth of one of those. A single star getting torn apart as it's got too close to that supermassive black hole. These astronomers were looking here at ARP 299, that's a Hubble image of that. And it's both a starburst galaxy, so you see a lot more star formation when you have colliding galaxies. It can sometimes trigger lots of star formation, but this one, for some reason, they were seeing a bunch of supernovas in. So they were looking for supernovas and supernova remnants. And what did they see? All these little boring blobs, but these boring blobs tell an astounding story. So first they saw this bright thing and they thought, oh, wonder if that's a supernova. And they went back and looked a few years later to see if it had changed. And it not only had changed, it was not so nice and compact and organized, it was getting stretched out. And they looked again and it went from being stretched out to being spit out. So it's not immediately obvious when you look at this set of little blobs, but they were able to analyze the motion and the change and evolution in these radio blobs to tell the story of this tidal, that tidal disruption to create the first little burp of a radio galaxy. And again, it's because of the VLBA's astounding resolution that we were able to make that observation. And if all of this hasn't been enough, I'm going to leave you with the dreams that these observatories have inspired. The VLA is celebrating its 40th anniversary. We'll be 10 years into ALMA next year, and it has only inspired us to want more. We have that aperture fever. We want more sensitivity. We want more light gathering power. And this is the dream that we have for the next generation VLA.
The idea for a next generation VLA was inspired by the VLA itself and the Atacama Large Millimeter Array in northern Chile. The NRAO, in conjunction with our science community, envisioned the NGVLA as a new large radio interferometer that will open up new discovery space in astronomy. Our idea for this is an instrument that is 10 times the sensitivity and 10 times the spatial resolution of the VLA or ALMA.
I am very excited about the data that will come from a next generation VLA. It will be exquisite in detail, the sensitivity will be unparalleled, and the opportunities that it will open up in many different science areas is really one of the things that excites me most, that this is a very open facility that anyone who has a great science idea can propose for and use, and its flexibility and its versatility enable many more science questions to be addressed than what we can think of right now.
The next generation VLA has been designed to accomplish 5 main science goals: unveiling solar system analogs, probing the initial conditions for life through astrochemistry, charting the assembly, structure, and evolution of galaxies over cosmic time, perform fundamental tests of gravity, and understand the evolution of black holes.
One of the things I work on is measuring the distance to stars in star-forming regions, and measuring their distance and how they move within the star-forming regions. Currently, we can only do 20, maybe up to 100 stars in these star-forming regions. Star-forming regions contain thousands, tens of thousands, hundreds of thousands of stars. With the next generation VLA, we'll be able to study 10,000 stars in these star-forming regions, which will help us give definitive answers to major questions in star formation.
The NGVLA will be a superb black hole hunting machine, the ultimate black hole hunting machine. The NGVLA's high-resolution imaging, combined with its fast mapping capabilities, will enable it to search for radio transients associated with gravitational wave sources, neutrino transients, and optical observatory transients, and identify those with black holes that are involved in violent merger events.
So that's a little promo video that was done for a big physics conference, but it reflects, I think, the excitement that the astronomy community has for our facilities and what we could do if, I mean, it's crazy. When they said 10 times the sensitivity and 10 times the resolution, they're talking about 263 dishes, not just 27 dishes of the VLA. They really are talking about 10 times that many, spread out all over New Mexico, into Texas, into Arizona, down into Chihuahua. I mean, they're really thinking big. And I think the budget will determine what is possible. But I think I've bubbled enough. You can tell I'm enthusiastic about all the new astronomy I'm learning from our radio observatories. And I'd like to thank you all for your attention. And I want to thank Nan. I saw she was helping answer some of the questions in the chat there. Nan does our social media.
Well, Suzy, thank you so much. That was really awesome.
It's a bit of a marathon. I kept trying
to become, great.
Believe it or not, it was almost twice as long before. And it's like, no, okay, Suzy, don't talk about that. And I kept trying to just pick what are the really great science cases that showcase what radio astronomy does differently.
Yeah, well, you did a fantastic job. And I hadn't heard of some of those more recent discoveries. I'm especially thrilled to hear about the one with the triple star system and the planets. That is so cool.
Isn't that?
Yeah. Well, I want to give everybody an opportunity to ask you some questions, if that's okay.
Sure.
So if anybody has any questions for Suzy, please feel free to unmute yourself and go ahead and ask them. And after we finish up with the Q&A, we'll do those door prizes and raffle drawings.
And I just put a bunch of links in the chat if people want to click away at those so that you've got them. It is the link for the interferometry app. One I didn't highlight is I talked a lot about creating composite images, and we have a colorizing app where you can create your own color versions of some of these images. So that's the colorizing app. The anatomy of the VLA antenna is that one that was clickable where you could roll over and see the different parts of it. And then the top 10 videos, there's 10 of them. You saw a couple of them here. So I did the link for all of those top 10 videos of ALMA's discoveries from last year. And we've also created some printable posters based on some of those discoveries. So all of that is in the chat now. But now I'll shut up and see if anyone has any questions.
Oh, this is Mott Given. I have a question. Can you hear me?
Yes. Hi, Mott.
My question is, with all the fires on the West Coast now and all the smoke in the atmosphere, does that affect your radio telescope observatory in New Mexico?
It does, and it depends on the frequency that we're observing in. So just as I showed that time lapse where we were observing through the clouds and the rain, there are some wavelengths that don't make it through water. So there are some observations that we can't make when it's raining. There are some observations, some frequencies that would be scattered by that smoke. But one of the cool things about radio is that it then generally sees through dust, right, out in the universe. So it's only at the highest frequencies that we can't observe because of the smoke.
Thank you.
I don't think I put in the chat our webcam. There's nothing to see right now because it's dark, but the VLA webcam, I've been watching that because one of our dishes is out just beyond, is just outside of the service barn and going to get moved back into circulation. So they'll take one out of the array and then put this one back in. And I saw the transporter parked near the one that's on the master pad there. And so I've been keeping an eye on it. And when you look, did I get that in there? If you look at the webcam, you'll see the, I didn't get it in there. Oh, I see what I did. You'll see that it's a smoky sky. It's not raining, it is smoky. If you take a look tomorrow, it's been really icky skies, not the beautiful blue skies that I love to see out there. Virginia skies have been very rainy lately. So I've been trying to go to New Mexico virtually with our webcam. And lately it's been very smoky gray skies. But they're still observing. So you'll still see the telescopes moving and moving to different targets. Any other questions? I overwhelmed you all. With a fire hose of information. Steve.
Deb, what is the ETA on the very, very, very large array? When do you hope to have it done?
So this year is when the astronomy community, the professional astronomy community, is doing what they call their decadal survey. So every 10 years they survey the community to find out what their priorities are, both for space and ground missions, and to find out what the next level of really support is needed to make that next breakthrough discoveries. And that survey is going on right now. So if we get a great recommendation for the NGVLA in that decadal survey, then we'll start asking for the money. So right now it really is just a dream. We haven't begun to build anything. We have put in some proposals for some design and development money. So that animation that you saw was based on real ideas, right? They think they want an 18-meter dish, not the 25-meter dish that the VLA is. They want the smaller 18-meter dish. They want the off-axis. It's not going to be moving around on railroad tracks like the VLA does for the different configurations. There will be so many dishes out there that they'll actually be able to divide it up into subarrays. They can use just a few dishes for an observation, or you can use all of them for an observation. And they've done all of those calculations, and they've been doing a lot of the very detailed engineering work to design them, but we haven't even built a prototype yet. So if we get a good recommendation and then we can get the funding, it still is 10 years off.
Thank you.
A lot of ifs in there.
Any last questions for Suzy? All right, well, let's do some door prizes and some raffle prizes. We'll do the door prizes first. The folks at the NRAO generously donated some really cool posters for us to give away. I'm going to share my screen so I can show these to you. They were made by an artist and astronomer by the name of Tyler Norden, who was actually out here for the total solar eclipse 3 years ago. He actually gave a presentation for Wyoming stargazing at our eclipse party.
Tyler, isn't he amazing? I mean,
such a cool guy. Yeah.
Oh, what I didn't know is that he did his thesis with VLA data.
Oh, cool.
How great is that? So I was thrilled when we could reach out to him and ask him to design observatory posters for us.
That's awesome. And he also did similar posters for, I think, every national park.
Every national park, yeah.
Yeah, and they're amazing. They all kind of have this retro look to them. They're so cool. Yeah. So we've got these 4 to give away. So we'll do 2 for the door prizes, and then we'll save 2 more for folks who have already bought raffle tickets. So I'll pull the first 2 lucky door prize winners.
Good luck. Yeah,
the first one, we'll do the one on the left here, the VLBA one first. And that one goes to whose ever screen name is my iPad. So whoever you are, what you need to do is just send us an email with your mailing address. You can send it to info@wyomingstargazing.org. Send us your mailing address, and we'll send that poster to you. So you've got the VLBA. I'm just going to mark that on your ticket.
So that one, we just talked to Tyler about these, and at the end of the month, we're going to do a Facebook Live with Tyler, and he was saying that he really was inspired by St. Croix to do that VLBA dish, because some of them are in kind of boring places, but St. Croix is kind of an interesting place, so that inspired that poster.
All right, and so for this next one, we'll do the one in the top center here, the Big Bang.
And that's for the NGVLA.
All right. So the lucky winner of that one is Mott Gibbon. Congrats, Mott. So yeah, just send us your mailing address to info.
Thank you.
Yeah, info@wyomingstargazing.org, and we'll get that to you. Write that one down here. And we do have 2 other door prizes. I want to show you what they are before we draw them. So can you guys see those stickers now? I need to switch my screen. Okay, I'm seeing some nods. That's good. So we've got some eclipse stickers, appropriate to connect back to Tyler Norden being out here. These eclipse stickers were designed by some local artists here in Jackson, Holly Sage Art. We've got a couple of those stickers to raffle off. First one is going to go to Janet. Congrats, Janet. Just send us your mailing address and we'll get that to you. For some reason, none of my pens seem to like to write on these raffle tickets. There we go. Now I got it. All right, and we're going to do one more. We also have these incredible prints of deep space objects taken by one of our board members. And he's generously donated a bunch of these prints for us to sell and give away. And we've got a bunch of these that we'll raffle off. Do the Lagoon Nebula. For some reason I can't pull the picture of it up right now. Not sure what's going on there. Very strange. Let's see if I can go to one of the other options so you can actually see what it looks like. Not sure why that didn't work. Apparently we've got a little bug in the system. All right, well, I'm not going to be able to show you the large prints right now, but they are they're pretty awesome. They're 2 feet by 2 feet, and we'll mail those to you as well. So the lucky winner of one of those prints is Barney. Congrats, Barney. All right, and now the raffle prizes for the folks who bought raffle tickets. We'll do the 2 other posters by Tyler Norgden. Do the one in the bottom center first. Lucky winner of that one is J.R. Dolby. JR bought a ton of raffle tickets about a month ago, so he's cleaning up on all these prizes.
That's our VLA poster.
Nice.
That you're only seeing a piece of it there.
Yeah. All right. We'll do the ALMA poster now.
I didn't mention it, but the ALMA Observatory is closed right now because of COVID in Chile. It's such a remote observatory. There's a lot of travel involved in getting employees up there, and travel just isn't safe in the country right now. So it is shut down for observations for the near future.
That's too bad. So the lucky winner of that last poster is T. Hobbs, I think it is. I don't think they're with us tonight, but I've got their phone number here, so we'll get that to them. And then we also raffle off another one of those deep space astrophotography prints. And the lucky winner of that additional print will be Steve Singer.
All right.
All right. Well, again, everybody, thank you so much for being here. We really appreciate you supporting Wyoming Stargazing by attending these events. Wyoming Stargazing is a not-for-profit organization. We're actually in the middle of a big community fundraising event right now. We get a 50% match on all donations through September 18th. So if you feel so inclined to support us with a monetary contribution, I'm going to put the link to do so in the chat room, or the chat box, if I can find it right now. For some reason, I need to stop my share so I can do that. There we go. There's the link to donate if you feel so inclined. But again, we really appreciate you being here with us. And Suzy, thank you so much again for being here. That was an awesome presentation, and we really appreciate you helping us out. We've got a little thank you gift that we're going to send your way as well.
Well, thank you.
Thanks so much for being here.
And I was lucky enough not to have any feline help until the very end.
I don't know if you saw, my dog decided to photobomb
yes.
a while ago, and my cat's been walking around as well. Common occurrence in the virtual world that we find
in the Zoom world.
Yeah. Well, again, thanks everybody for being here, and have a fantastic night.
Yes,
See you next time.
Great presentation.
Thank you very much, Mary.
Thank you very much.
You're very welcome.
Good night.
Good night, everybody.
Good night.